Okay, let's get started today's class. So, hi guys, I'm recording this video in the hotel. So, I hope my voice is maybe recorded well through my Bluetooth device. So, let's get started. So, in the previous class, we learned about how to handle data hazard. Okay, so in order to handle data hazard in the pipeline processor, so we firstly detect the data dependencies, and then once the data dependency is detected, then we can forward the data to the input of the ALU, or if the previous instruction is the load instruction, then the we can sometimes and then the following instruction, the very next instruction requires the result from the this load instruction, and we cannot put the data from the load instruction, right? And in this case, now we need to detect the data hazard using the hazard detection unit. Then we need to store pipelines. That's what we learned, right? And then now, so we will learn about how to handle the control hazard, right? So what is the control hazard? Control hazard. So, so I mentioned that the control hazard means that the clock cycles are wasted due to control instructions. The control instructions include branch instructions, jump instructions, and then exceptions, right? So control hazard represent the waste of clock cycles because of these branch instructions, jump instructions, and exceptions. Then why? Why the clock cycles are wasted by these instructions? Let's think. I will take the example of branch instructions. Okay, so this is the example of instructions. So you can find the PQ here, right? And then also you can find the next instructions like add or an add instruction, right? So then also this number, what is this number? This number is PC, PC of instructions, right? So the the PC of the PQ is the 40, right? So actually it's 32, right? So and then so if you see that this big instruction, then you can find that so if the condition is true, then we need to jump to the 40, 40, 40 plus 32, right? Then we need to jump to this instruction, the load instruction, right? But if the branch condition is false, then the next instruction will be executed. But this is the pipeline processor, and then let's see how these instructions are executed in the pipeline processor, right? So this is the clock cycle number, right? So in the clock cycle number one, so at the clock cycle number one, the branch instruction is in the instruction fetch stage, right? So here, and then in the next clock, right? The next clock, the branch instruction is propagated to the ID stage. Then which instruction will be fetched? The next instruction. So actually, so we don't know. So branch instruction is in the ID stage, right? Oh, I see. The ID stage, right? Second. the branch instruction in the idle stage. And then we don't know the result of the branch instruction, right? So the next instruction will be fetched. What is the next instruction? The PC plus 4. The correct PC, the PC of the branch instruction is 40, and the pipeline processor will fetch this end instruction. So end instruction is in the instruction fetch stage, right? And then the clock cycle number 3, then branch instruction is in the execution stage, right? Then when the branch instruction is in the execution stage, what is performed? We need to perform x1 minus x0, right? So when the branch instruction is executed, the ALU performs sub instruction, right? Subtraction, actually, subtraction, right? So, and then at the rate time of this EX stage, then we can get the result of the branch instruction, but it's too late, right? So if the x1 minus x0 is 0, then the branch is true. But this condition is determined the late timing, the late timing of the execution stage. So when the branch instruction is in the execution stage, then the end is in the idle stage, and then the next instruction or is in the instruction fetch stage, right? So the result of the branch instruction, right? The result of a branch instruction is 0, right? So 0 is propagated to the memory stage, okay? So then if the 0 is 0, right? No, 1, so which means that uh, it means the x1 minus x0 is 0, right? So it means that the branch condition is true, right? So the branch is determined. So the result of a branch is determined when the branch instruction is in memory stage, right? So it is you need to understand this. So determined when the branch is memory stage, right? Because as I mentioned, the zero so actually the ALU consumes some time for executing the subtraction, right? So the zero is determined at the late timing of this execution stage. So actually the zero needs to be propagated to the next stage, the memory stage. So we can say that the branch is determined in memory stage. Okay, so zero is here. So when the branch is in the memory stage, then the add instruction is also fetched, right? So, and then, we can find that our branch is true. So if the branch is true, then the branch condition, the branch result is given to the PC, right? So we can find, so then the PC is updated by PC plus, let's say, this immediate, right? Offset. So this is the new PC. So when the new PC is reflected, the new PCE is reflected in the next cycle, right? So the branch is in the write back stage, the branch is here, then we can find that the new instruction, the target of the branch instruction, the load instruction is fetched, right? So the target of branch instruction. And the branch instruction is write backstage, right? So this is the correct instruction. The branch is here. How about these instruction? So, uh, so in this example, so we can find that these three instructions and or and add instructions. So these instructions are fetched, right? Those instructions are fetched. Those instructions are fetched. Oh, I need to use this. A second. So those instructions are fetched, but you can find that. So this load instruction is the correct instruction. So, and then those instructions are in the memory stage, uh, execution stage, and ID stage, right? But what's the problem? These instructions are invalid instruction. Why? These instructions should be executed if the branch result is false, right? Well, the branch is, what is the result of the branch instruction? The branch instruction is true. So it is called taken. The branch is taken, right? So because these instructions are incorrectly fetched, so we need to cancel these instructions. So what does that mean? We need to cancel. We need to cancel these instructions. So how many instructions are canceled? Three instructions. Three instructions. Like so, and or add instructions need to be canceled. Okay. So because three instructions are canceled, if the branch is taken, that means the condition of a branch is true, then the three cycles are wasted. Why? So it is because the branch is determined. Okay? The result of a branch instruction is determined in memory stage. So the incorrectly fetched instructions are in the instruction fetch, ID, and execution stage. So, and then we need to cancel these instructions, right? So that's why the three cycles are wasted, right? So, you can find that the branch is applied when the branch instruction is in the write back stage, right? And then what's the problem? The problem is that if the branch is taken, then this pipeline processor wastes three cycles. Okay, so this is a huge, right? So for example, think about the for iteration, right? Like for I equals 0, I is less than 100, I plus plus. So what's the problem? So in order to execute this for iteration loop, then we need to repeat this statement, the inside of the for loop, 100 times, which means that the branch is here and branch is taken 100 times. And then for each branch instruction, whenever the branch is taken and three cycles are wasted, it's a huge. So in order to handle the control hazard, then reduce we need to reduce the wasted cycles. The wasted cycles, the cycles wasted by branch instruction. Then how? And how can we reduce these wasted cycles by branch instructions? And what was the problem? What was the problem? What is the problem of these wasted cycles? Because branch is determined in memory stage, right? So the the problem is that the branch is determined late. This is the problem because the branch is determined in the memory stage. Then when the branch is taken, we waste 3 cycles. And what is the solution? The solution is that, oh, if the branch is determined earlier, then we can reduce the wasted cycles, right? And how? The solution is that, oh, the problem is, oh, the branch is determined late. And what is the solution? Then if we can determine the, the result of a branch instruction earlier, then we can reduce the wasted cycles, right? And how can we determine the result of a branch instruction? How? So actually, you know, actually, we assume our pipeline processor only supports the PQ, right? Then what is required in order to perform the PQ, right? X1, X2. Then we need to check the equality between the two register operands, right? We can just check the equality between X1 and X2. And how? Actually, so in order to check the equality between two operands, we use ALU, right? And then ALU performs the subtraction, right? So, right, we just performs x1 minus x2 in this example, right? But think about this. So how can we check the equality between the two numbers? So, and then these numbers are binary numbers. So, for example, 1011 and then 1011. So we need to check the equality. So in order to check the equality between two numbers, then we can check, firstly, we can check the equality of 2-bit data, right? How can you check? We can use the exclusive OR gate, right? So because we use the exclusive OR gate, and 00 is 0, 01 is 1, 10 is 1, 11 is 0. So actually exclusive OR detects if the 2-bit numbers are different, right? So we can use the exclusive OR in parallel for these bits, right? And then if the one of this equality check is 1, at least the one equality check result is 1, then it means is is the two numbers are different, right? So when you check the equality between these two bits using the exclusive OR and then all results are 0, then we can check that, oh, these two numbers are equal, right? But if not, then uh, the one of these equality check bit bit equality check is 1, then it means our two numbers are different, right? And what does that mean? We can just use the exclusive OR gate to check the equilibrium between the two bits, and then if all these comparison results are zeros, then it means two numbers are equal, right? So we need to detect the all zeros. How? We can use the NAND gate, right? So we don't need to use subtractor. So what is the problem of subtractor? So in chapter 3, we learned how to perform addition, right? And then you know the subtraction is just the addition, right? So right, because we can just invert the the second operands, and then we can just add the one, right? It's a subtraction. So actually the subtraction is equivalent to the addition. Then what is the delay of this addition? So delay of addition, like actually when we perform the addition, then carry is propagated, right? Carry is propagated, and then so the final result, like this MSB result, is determined late. That's the problem, right? But if we just perform the equality check, right, then like we can check the equality of each bit in parallel, so we don't need to uh, deliver carries to the next digit. We can just perform this exclusive OR in parallel, simultaneously. Then we can just detect the all zeros using the NAND gate. Okay, NAND gate. So it's very fast compared to this addition, because addition is slow because carry needs to be propagated. But equality check is fast because parallel comparison between two bits is possible, right? So we can implement the equality check logic, and very simple equality check logic, and then this equality check logic is very fast, right? So what does that mean? So what was the problem? The branch is determined late, but we can just check equality between two numbers very fast. So solution is, we can just check the result of a branch instruction. So actually the result of a PQ, because we can just check the equality. So we can just add a new comparison unit just after the register file. So that can be the solution, okay? Because so the problem is the branch is determined late. So the solution is that we can just detect the result of a branch instruction earlier by using equality check logic. So in this solution, so if you see this solution, you can find that the equality check logic is just after the register file. And then, as I mentioned, this equality check logic is very fast, right? Compared to uh, the addition, adder or subtractor, this equality check logic is very fast. So it means we can just get the result of a branch instructions in ID stage, because the equality check logic is in the ID stage. And then, oh, we know. So branch is, so in this solution, by using this solution, branch is determined in ID stage instead of, so originally the branch is determined in memory stage, right? So, then when the branch is determined in memory stage, then if the branch is taken, 3 cycles are wasted. But if the branch is in ID stage, then and the branch is determined in ID stage, then 1 cycle will be wasted because only the instruction in the instruction fetch is incorrectly fetched, so we can just cancel this instruction. You understand? So what is the solution? Solution is that the branch can be determined earlier. Okay, so by using this simple equality check logic. Okay, so then so which means so in this example the branch is here and then the instruction is here, the next instruction. So then the branch is taken, then only this instruction will be cancelled, right? So branch is here, and then the next is the target of the branch instruction. The target of a branch instruction will be fetched earlier, and then only the 1 cycle will be wasted. Okay, but I don't like this solution. Why? What's the problem of this solution? So actually, if you read the textbook, so actually, and you know, the reading a textbook is very, very important. Okay, so you need to read, you need to study by reading your textbooks, right? So anyway, so if you read the textbook, then you can find that this is the solution of the branch, the control hazard by branch instruction. But I don't like this solution. Why? So actually, well, this problem is uh, so this problem is what is corrected in the second edition of this textbooks actually. So uh so you can find that the branch instruction receive two register operands, right? And then so actually you can find the data coding box. The data coding boxes are in the execution stage. So think about this: the add x1 and then when pq x1 x2. So this is the destination register of add instruction. And then so actually when the branch instruction is executed, so which means that the subtraction is performed by ALU, the result of add instruction can be forwarded to the ALU, right? Because the boarding boxes are located before the ALU, right? But in the new solution, the branch instruction reads register operands from the register file, and then two register operands are checked by this comparator. What's the problem? This so actually data cannot be forwarded by this forwarding unit. Okay, because the folding boxes are here. So the problem is that for this case, data folding does not work. So if we just improve the performance of branch instructions like this, the problem is that actually this solution creates new data hazard. So this is the problem, right? So then if because the data folding is not possible using the existing folding unit, then what's the problem? It cannot be handled by the existing the folding unit. So which means in this case the PQ needs to be stalled. Okay, stalled until the result of add instruction is in the write back stage. Okay, you understand? Because what's the problem? This branch instruction cannot use the data folding box multiplexers. Okay, so it will create the new data hazard. Okay, so that is the problem. So in the second edition of the textbook, we also add the solution. So we can just add the new data folding path, but I don't like this. Okay, so another possible solution is that so we can just use the dedicated branch unit. Okay, so we can use the simple comparator. Well, we can use the simple subtractor to implement the BQ, BNE, BLT, and BGE. Okay, and then this is just the comparison unit. Okay, so so as I mentioned, the comparison is okay, right? And then compared to the ALU, the delay of the comparison unit is lower. Okay, the delay is lower. So, so another possible solution is that the branch unit is here, and then in this solution, the branch unit can receive data from the data folding multiplexer. Okay, so you can find the folding multiplexer here, or here, and here, right? Then you can find that the output of data folding multiplexers are given to the branch unit. So if the branch unit is in the EX stage, then we can make use of the data folding path in the pipeline architecture. Okay? Then what is the penalty? What is the wasted cycles by taken branching? The branch is taken. So in this solution, when the branch unit is in the EX stage, then branch is determined EX stage. Then two cycles are wasted. The branches are taken, no penalty. Just it's the same. But this solution does not cause new data hazard. Okay, so when we design the five-stage pipeline architecture in the lab assignment, then actually we will be requested to design the branch unit in the EX stage, like this solution, right? So, so it's a simpler. It's a simple. It's actually we don't need to design the new data folding unit or new hazard detection unit for, for this solution, right? So actually in the lab assignment we will implement this 5-stage pipeline architecture. Okay, so which means the branch unit is in the EX stage. Okay. Okay, so this is the some discussion about handling the control hazard by taken branch. Okay, but still the clock cycles are wasted. And how can we handle these performance issues by branch instruction? So as I mentioned, this is very critical, right? The the branch instructions actually, so you can think that, oh, just the 2 cycles or at least 1 cycles, just the 2 cycles are wasted. But so as I showed the example, like this iteration loop, so actually we can find the many taken branch instructions in our code, right? And then let us assume, okay? So if the taken branch waste the 2 cycles, then it's huge actually. And how can we reduce how can we further reduce uh, the penalty by the branch instruction, like take a branch? We can apply the prediction, branch prediction. So what is the branch prediction? So which what should be predicted? Okay, the branch prediction. What was the solution? What is the problem of the branch instruction? Why the clock cycles are wasted? Because the branch is determined late. So I mentioned that this is the problem, right? This is the problem of the the penalty, the control hazard by branch instruction. And what is the solution? Solution is, oh, we need to determine branch instruction earlier. So we discussed some several solutions, right? So like the dedicated branch unit or the comparison unit, right? But it still waste several cycles, right? This is the problem. So another possible solution is that we can predict what? Predict. We can predict the result of branch instruction. So it's a prediction. And then when is the prediction is good? So we can predict some result, right? By some probability, right? So let us assume that, oh, the branch is taken, so some future event. So let us assume that we can predict some future events, right? So let us assume that we can just predict the future event correctly 90%, and then the 10% our prediction can be incorrect. So if we can predict the future result with a very high probability, then we can use this prediction technology in our system, right? So if the prediction rate, so it's called the prediction hit rate. So which means that if the prediction is correct, then it's called the hit, right? And then if the So prediction is incorrect. This is called the miss. Prediction is missed. So if the hit rate is very high, then we can apply the prediction in our system. So, so I mentioned that we can predict the result of a branch instruction because this is the prediction, then which means that we can just predict the result of a branch instructions earlier. Right. So if this prediction is true, then it's just good. Okay. Then if the prediction is incorrect, then we can just cancel the incorrectly fetched instruction, right? Because then we learned that the performance of the clock cycles are wasted if the instructions are incorrectly fetched, right? So this is the benefit of a prediction. If the prediction rate is very high, right? If the prediction is correct, so which means that it's a hit, then it's good. The prediction is missed, so it's incorrect. It's it's not good, but it's the same. So it means it's better. Okay, so it's better. But then if the prediction is missed, same, right? And then the, we can predict some result with a very high probability. And is it good or bad? It's good, obviously, right? Prediction is a hit, it's better. Prediction is missed, same. The penalty is the same. And then if we can predict the result with a very high probability, then we can apply the prediction technology. So this is the prediction technology, right? So we don't know that we don't know the future event exactly, right? But we can just predict. We can predict the result of the future event with a high probability. Then the French prediction, actually, the prediction rate is very, very high, right? So, and if we just apply some prediction technology for the branch instructions, then for the hit case, then it's better. We can just waste the fewer cycles. Then if the missed, then it's the same. The penalty is the same. In this case, then we can apply the prediction technology in the pipeline architecture, right? So, and then this branch prediction is called the dynamic branch prediction. So what is the meaning of the dynamic? So what is the opposite meaning of the dynamic? Static. So dynamic, what is the meaning of dynamic? Dynamic. What is the meaning? The meaning is that we can predict the result of a branch instructions in runtime. So by monitoring the event of branch instructions in the system. So steady means it's just fixed, right? Steady means it's already fixed. So actually we can just apply the fixed prediction result to some uh, prediction technology. So we will learn about the dynamic prediction. So dynamic means that so in runtime the CPU monitors the result of branch instructions, and then by analyzing this history of branch instructions, then the CPU predicts the result of a branch instruction in runtime. So this is the meaning of dynamic. So we will learn about the dynamic branch instruction and how. Think about the for loop. So for I is 0, I is less than 100, I plus, and then some blah 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 blah, and then this is the for loop, right? The example of a for loop. So, and then I mentioned that the branch instruction is here, like some BQ, and then if the branch is taken, then we return to the first instruction of this for loop, right? So what does that mean? It's taken. The branch will be taken. How many times? 100 times, right? And then as I mentioned, we can just observe this type of for loop in our code frequently, right? So then how can you predict this result of a branch instruction? Oh, branch is tick, 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 tick. And then the 100 times, then 100 times of iteration, then branch will be not taken, right? So how can you predict? Oh, if the branch is taken once, oh, then the next iteration, so we can just predict that, oh, branch will be taken. Oh, this is taken again, and then oh, we've taken. We can predict the result of branch instruction like this. So that means you can just check one previous result, right? So taken. Oh, when we monitor the result of a branch instruction, which means the history of a branch instruction, oh, it's taken. And what's the next result? What will be the next result? We can predict the next result can be taken again, and then taken. So which means, oh, once the branch is taken, then we can predict, oh, it will be taken again. Okay? So this is some example of a branch instruction, right? So what is required? We need to monitor the event of a branch instruction, which is the result of a branch instruction. So this is the previous event, right? And then based on the monitored branch event, we can predict, right? So what is the result of branch instruction? Taken or not taken, right? So we can just select the result of a branch instruction from taken or not taken. Okay, so this is the dynamic branch instruction. Okay, so then how can you apply? So I mentioned that firstly we need to monitor. What does that mean? It means we need to store the result of branch instruction. But there are many branch instructions, right? So it could be BR branch instruction 1, branch instruction 2, branch instruction 3. So we need to identify these different branch instructions. How? We can use the PC, right? Because each instruction is mapped to its own program counter, right? So using this PC, so like this is the PC of the branch 1, and then PC of the branch 2, PC of branch 3, blah, blah, blah. So based on the PC, we can identify the branch instruction. Then we just store the result. So actually, what is the result of branch instruction? Hmm? What is the result of branch instruction? I don't know how. So, okay, I don't know why it's erased. So PC of branch 1, PC of branch 2, because we can just identify branch instruction using the PC. Okay, so we can make the table, and then we can just only store the, the history, the result of a branch instruction. Then actually the branch instruction result is taken or not taken. So maybe it's 1, it's 0. You can just represent the taken as a 1, and then you can represent the taken as 0. So we can just store. So 1, 0, 0, right? And then, so the 1, if we just store the very past, the very previous, the result of a branch instruction, there's only one, and it is called the one-bit predictor. So because, so it's a one-bit predictor because we just store the one previous result of a branch instruction. Then, with the one-bit predictor, if the previous result is taken, right, then the next, we can just predict the result of next branch instruction as taken, right? So when it's not taken, then we can just predict the next result of our branch instruction. The result of next branch instruction is not taken. Okay, so which means if the branch is fixed, then we just read this table using the PC, right? Then we can get the result of a branch instruction, right? So it's 1 or 0. And if the 1, then we can just predict, oh, the result of branch instruction is 1. If the prediction table includes the 0, then we can just predict that the result of the next branch instruction is not taken. Okay. So I mentioned that we can just read this table using the PC, right? So this is called the branch prediction buffer, PPB, because this is a table, right? So it's a table, then we just store the previous result, the result of a previous branch instruction. So it's called the buffer. It's a temporary memory, right? So this is called the PPB, right? And then branch prediction buffer is in the it's accessed indexed by PC. So the branch prediction buffer is in instruction fetch stage. Okay, so this is the branch prediction buffer. So we can determine. So because when we apply the branch prediction technique, then our branch prediction buffer is in instruction fetch stage. So which means, we can just predict the result of a branch instruction is in when the branch instruction is in instruction fetch stage. Understand? Right. So which means if the prediction is correct, then there is no penalty. Clock cycle is not wasted because the prediction buffer is in the instruction fetch stage. Okay, but if we just use the one-bit predictors, and one-bit predictor just monitors the the the, the one previous result of a branch instruction, right? And what's the problem? The prediction rate. The prediction rate may be low, right? So this is the example. So, so we also frequently use the nested for loop, right? Like the for equals 0, I less than 100, I plus plus, and then for j equals 0, j is less than 100, j plus plus, right? These are nested for loop, right? What's the problem? So when we just check the sequence of a branch result, so there are two branch instructions here. So this is the branch instructions for the inner loop, then this is the branch instruction for the outer loop, right? Then the problem. For the inner loop, the branch will be taken, not taken, right? It's a final iteration. Then the outer loop will be repeated. So taken, and then not taken. So what's the problem? If we use the one-bit predictor, it's incorrect for this case, right? It will be predicted as taken, but the real result is not taken. And then with the one-bit predictor, oh, the next result will be taken, but we can just predict that the next result is not taken because it's a one-bit predictor. We just detect that the result of the branch instruction is not taken. It's a previous result. So we can just predict the next result is also not taken, which it's missed here and then it's also missed here, right? So inner loop branch mispredicted twice. Okay, and we can just handle this issue using the 2-bit predictor. So this is the state diagram of the 2-bit predictor. Okay, the 2-bit predictor is composed of 2-bit the accumulator, right? And then it is saturated, right? So let us assume that it's not taken, it's a 0, and then if the branch is taken, then it's increased by it's increment by 1, and then it's a 1 0, it's 1 1, but it's saturated. Also, it is saturated in the 0 0, right? You can find here, so here. So what does that mean? Once it's and then we just predicted this if the number of this uh PPB buffer, the branch prediction buffer is 1 1 and 1 0, then we can just predict the result is taken. And then if the number is 0 0 and 0 1, then we just predict the result of a branch instruction can be not taken, NT. So then it means with the 2-bit predictor, it means that we just monitor the one more event, right? Then by accumulate. So which means that 2-bit predictor means if the some events is repeated, so some events happen consecutive, so same events happen consecutively, then we can just predict the future event based on this consecutive result. Okay, so which means not to predict the taken, which means the actually the previous events need to be taken and taken, right? So this is the two-bit predictor. So we can just start. So with the two-bit predictor, we can just start from the 0, 0, the initial value. So and then for example, in the for loop, so firstly it's 0, 0, and then what is the result? It's taken. So it's missed, right? You can start from the first loop, first iteration number 1, 2, okay, so for loop, then this is the iteration number. So we can start from the 0, 0. So this is a prediction. Then this is the hit or miss. Okay. So first is the 0, 0. The predictor is not taken, right? And then it's miss. So it's missed. So incorrectly predicted. And then because the event is taken, as real event taken, it's a missed. Then because it's taken, then it becomes the 0, 1. Then what is the predicted value? Not taken. It's predicted as not taken, but the real event is taken. It's a miss. And then it becomes the 1, 0. Then the taken, the hit, 1, 1, taken, hit, and then still 1, 1, taken, hit, right? And then at the end of the iteration, it's a 1, 1, but it's a predicted as taken, but not taken. Then it's a missed. Okay? For the one iteration loop, then we can also calculate the prediction rate like this. Okay? But for the nested loop like this, okay, then at the end of the loop, it's a 1, 1, it's a taken, and then but it's not taken, so it's a missed, right? But and then so here, and then for the next iteration, it becomes the 1, 0. It's just still taken. It's a taken and it's a hit, right? So for the nested loop, and then for this case, and then we use the two-bit predictor, then we can just improve the hit rate of the branch predictor. So, in the two-bit branch predictor, for each PC, each entry includes the 2-bit. So with this 2-bit, then we can just implement this saturated adder, saturated incrementer. Then we can just predict the result instruction using this branch predict buffer. Do you understand? Okay. So using the branch predictor, then so I mentioned that we can just predict the result instruction. Then the result PPB BPB is in instruction batch stage. So what does that mean? So which means we predict, can predict the result of a branch instruction in instruction batch stage, right? So it looks like this with the PC. The PC is here. Then with the PC, we will just access the instruction memory. And then using this PC, we will also access the branch prediction buffer. Okay, then we can get the predicted result of the branch instruction. Okay, so we can predict, but also what is required? If the branch is predicted as taken, then we need to jump to the target of the branch instruction, right? So, which means we also need to know the target of the branch instruction, right? So even with the predictor, we still need to calculate the target, right? Then it's a 1 cycle penalty. Okay, so we need to know target and how. So we can predict the branch instruction result in instruction batch stage, but we don't know the target because the target, we can calculate the target in the ID stage. So still we experience 1 cycle delay for the taken branch. How can we handle this problem? We can also predict the target using branch target buffer. It's called the branch target buffer. So PTB. Okay, but target of the branch instruction is it's just fixed, right? Like so. Think about this: PQ X0, X1, and immediate. So and then we can just calculate the target of this branch instruction like PC plus immediate. Then this immediate number is just included in the instruction. So this is the static value. So once that we calculate the target of the branch instruction, then we can just use this the target of the branch instructions again and again. So using the branch target buffer, we just store the target. So PC1 target, PC2 target, blah blah blah, like this. And then once, as I mentioned, this is the static value. Okay, once it is calculated, it's the same for the future branch. So we can just store the target address of the branch instruction, target PC of the branch instruction, and then it is also indexed by PC. Okay, so we also use the branch target buffer in the instruction batch stage, then we can get the target. So by combining the result of the branch instruction, and then if the result is predicted as taken, then using this target, then we just update the PC. So then what is the penalty of if the prediction is hit, then the penalty of a branch instruction is 0. If the prediction is missed, right, then it's the same to the penalty of this missed branch prediction is same to the taken branch without branch prediction buffer, right? So if the hit rate is very high, then the penalty is 0. So using the prediction technology, then we can just handle the performance issues by the control hazard, right? You understand? So this is very good, right? So actually, in the CPU, we use many prediction technology, right? Then this is very critical for the performance of CPU. Okay. Also, as I mentioned, the branch predictor is very critical for the performance of a CPU, right? So you can just so so as I mentioned, the prediction is hit and no penalty. Prediction is missed, and then this penalty is the same to the original branch instruction. So that's why we use the prediction technology. Okay. So, this is also very important. So I hope everyone can understand this issue. Okay, so I will stop here. And then I hope everyone can watch this recorded video, and then everyone can understand the control hazard issues, and then how the control hazard issues can be handled by the prediction technology. Okay. Okay. So thank you for your attention. And then see you in the next class after I uh, come back to Korea. See you guys.